All right, everyone, thank you for joining us. I just wanted to welcome you all to our MESS series. If you've already attended these in the past, you kind of know what the deal is, but if not, welcome to your first MESS series. MESS stands for Methodology Seminar Series. But also because it is, it's an acronym for MESS, right? I also think this is made by and for grad students mainly to connect with faculty members, to connect with each other. And, you know, since grad students are always in a constant state of flux, learning, doing things, just a mess, right? I think MESS can be more than just an acronym. So we decided to go with it. First things first, if you notice on the left side, there's a bunch of tutorial stuff that you can find on our MESS website. All of those links are below. If you get a chance, if you could just sign in, that would be great. It's a very short form, just so we can get an idea of who's here and, you know, what brought you here. That would be great. Again, links, all of the links will be in the chat box. So before we get started with Hyemin's talk, I just want to take a chance to thank everybody. There we go. It's a large team who does everything. Each of them do different pieces. But since Jake is here, I just want to take a second to give a massive shout out to Jake. The website, if you get a chance to look at the MESS website, is amazing and so accessible, and everything is on there. So you can kind of see the work that this entire team has done over the years because of Jake's help to make it more visible. So thank you, Jake, and thank you everybody on this page. So if you know some or any of them, make sure to you know, let them know that their series and what they're doing is helpful to you, or not. If you don't have anything good to say, you know, don't say it. That's my that's my 2 cents. Usually I do this at the end, but because it's a Zoom session, I'll just let you guys know. We collect feedback. Again, this is a pilot series, so often we don't know what your needs are. So we're setting this up. Just take a moment after the talk to give us some feedback in terms of whether this helped you, what your needs are, what you want to learn, all of those kinds of things. And the special thing about this particular feedback form that I often don't see in feedback forms is your direct message to the speaker. So we've put a little piece in there, as you can see over here, right about arigato sensei. So if you want to let Hyemin know how he has helped, or you have some good things to say, you have that affordance right here. So again, the link is in the chat box after the talk if you want to take a moment to do that. So without further ado, let me introduce to you Dr. Hyemin Han, who will be doing a talk today on Bayesian analysis, specifically using JASP and ARM, or just JASP, because that's a more accessible GUI interface. But before he gets started, I just want to take a moment to introduce Dr. Han to you if you are not familiar with him or his work. Dr. Han is an assistant professor in the Educational Psychology and Educational Neuroscience program. He is also the PI of the SEED Lab, which stands for Social, Emotional, and Educational Neuroscience. He is very, very well published, as you can see, this list right here on the top right. That is not a comprehensive list, so I just had to pick and choose because there was a limited amount of space, but it just goes to show that he's very well published far and wide in a variety of journals. So, you know, you're in good hands here today. But before we get started into his research interests in the methods, which is of interest to you, I'm sure, I just wanted to take a chance to explain a little bit about these pictures that show kind of a duality, if you will, right? As you can see on the right, here you have Dr. Han, who is accepting awards from big organizations. So clearly he's celebrated, he does really good work. He's respected by his peers, right? But at the same time, he's very like fun and accessible, as you can see by that other picture right there, right? And because this is, again, mostly for graduate students to connect to faculty and interact with each other even, I just wanted to point that out, right? That if you wanted to kind of reach out to Hyemin, and what you'll find in him is a very accessible, very helpful professor. That has been my and many people's experience. So just wanted to put that out there, because I think mentoring is a big part of graduate students and graduate student experience. If you're here for the learning part of the methodology, even though Dr. Han will be teaching us a little bit about Bayesian analysis, I think what I want to focus on is this multidisciplinary research methods part. So he does research in MRI, he's done multiple meta-analyses, he uses a lot of deep learning techniques, he's done longitudinal analyses, and many other things. So what I do want to point out is if these are some of the methods that interest you, get in touch with Dr. Han. You can tweet at him. His lab website is in the chat box also, so you can reach out and look at his publications, email him through there. Many different ways. But again, the idea is we wanted to highlight all his research interests, right? Whether it is in morality or social development, growth mindset, educational interventions, or computer simulations, whatever it is that interests you. And if you think, oh, this is something that I want to learn a little bit more about, I want to do in my own research, you might want to get in touch with Dr. Han. Before I turn it over to him, this is something he wanted, a site that he wanted me to share. So of course, there's tutorials, but also if you want, just items that would have Bayesian stuff on it, cups or bumper stickers or what have you. It's all of it is on there. So tutorial and fun stuff. Again, the link is in the chat box now.
Yeah, thanks a lot, Mona. I really love your introduction. It's very funny and very informative. So I really appreciate that, your kindness and your attentiveness, etc. So let me stop sharing my video, because I'm gonna mainly focus on the slides as well as the materials that I have prepared, like a JASP tutorial and our tutorial. So I'm gonna show you the slides and then the tutorial materials once I share my screen. So thanks a lot for coming to my workshop today. It's like, oh, looks like I need to admit the folks who are waiting in a waiting room. Is it correct, Mona? Oh, the issue is that, even though like I can manage, but I feel like once I have to do two things, like giving a lecture, doing workshop, and then taking care of a waiting room, then that's gonna be a big mess. But that's okay. I can manage. So please I'd like to apologize in advance if I get distracted from the lecture or workshop, because once I have a new guest coming to the waiting room, then I have to manually admit the person into the Zoom meeting. So please, if you can understand that, then it'll be great, appreciated, because you know that nowadays the Zoom bombing is super crazy all over the world. So I heard a lot of horrible stories about how the Zoom meetings have been bombed by jerks, stupid guys. Like they came into the Zoom meeting, was a Zoom meeting using a kind of non-random, not password protected stuff. Then strange guys, strange jerks, strange stupid guys coming into the room and present something inappropriate during the context, and then the meeting is bombed. So to avoid that kind of issue, I feel like it's necessary to keep the waiting room. So if you could understand this situation, then it would be appreciated. Okay, so Mona posted a couple, yeah. Mona, do you have anything to say?
No, I just said thank you. Thank you very much.
No worries. Okay, so Mona just put lots of useful things like the links as well as my address on the chat window. So if you have any further questions, or like if you're curious about how to get the materials, then please refer to the links and materials that Mona posted. Also, before getting started, I would like to let you know that to save time and to minimize any possible distract, if you have any questions related to materials, then please type your question in the chatting window so that Mona and I can address the posted questions at the end of my babbling part. Okay, then let's get started. I'm gonna share my screen. Okay. Can you see the slides here? Oh, looks like I need to manually turn on the chat. Okay, thank you. Yeah, I realized that this is a pretty interesting setting because I thought that the majority of audiences are supposed to be students, but realized that now I have lots of my fellow colleagues, faculty members joining the session. So here's one disclaimer before getting started. If you expect something pretty super advanced, then I feel like you're gonna get disappointed at the end, because the main purpose of today's workshop is to just briefly introduce what the heck Bayesian analysis and then how to play with some basic Bayesian tests like a t-test specifically. So if you're interested in like a more advanced method in Bayesian analysis, then sorry, I will be able to arrange future opportunities by working with Mona. So that's my one disclaimer before getting started. Okay, so thanks again to come to my session early in the morning, Friday. It's pretty challenging. I know that after having a long day, then you have to take a good night's sleep. And then it gets pretty tricky to wake up early in the morning, Friday, TGIF, but you made it. So I like to appreciate your attentiveness and diligence. So today, I'm going to briefly talk about the basic themes of Bayesian analysis, and then how to do some very basic Bayesian analysis with some tools like JASP, JASP, and R. When I organized this Bayesian Bayesian method workshop at the beginning, I originally started only with a JASP because that's pretty feasible. GUI applied tool, very feasible and very easy to use, but realized that now we have to know how to play with the R, because the replication crisis has been a serious issue in the field of psychology and even educational research, educational studies. So the issue is that the point is that if we can do all the analysis with R, then this is that you have to create your own code to clean the data and then analyze the data. All the things should be written in our language. Then this is that you can share your data set as well as R codes with your colleagues and other scholars so that they can test, replicate what you did. So I realized that specifically during these days, adding some R components may be helpful. So even though that it takes a long while to fully understand how to play the R as a computer language, but just briefly showing you folks what the R is will be helpful to get you somehow familiarized with this new language. So I ended up with adding R to the workshop component. Okay, so let's move on. This guy, EJ, is a super awesome guy, Bayesian hipster. Yeah, for sure, he's a hipster because Bayesian guys are usually hipsters in the field. Anyway, this guy is the leader of the team that developed the JASP, which is available for free for everyone. So I'd like to express my appreciation to him at the beginning of this workshop. And then I like you to show these super adorable, cute guys, Bayesian canines. So basically, Bayesian, I'm gonna repeat the same thing later, but the basic rule of thumb of Bayesian analysis is that it's kind of pretty iterative processes. Once you start with your own prior knowledge, then you're gonna update your own prior knowledge, prior belief based on observations, and then ended up with having a kind of updated posterior probability or posterior knowledge at the end. So, sorry. At first, you're gonna start with this guy. This guy is a prior. You're gonna start with a golden retriever as a prior, and you do the observations like if you repeat to observe corgis, then the updated posterior is gonna be Jack Russell Terrier, half corgi, half golden retriever, still very active and very vigorous dog breed. So, as Mona introduced at the beginning of the lecture, you can download this picture from the provided link because the author of this book, Bayesian analysis book, released this picture, the free license. So if you wanna create your own corgi mug, corgi cup, or corgi decal to be attached on your car, then you are free to do so. No worries at all. Everything is free. All right, then let's move on to some features, good features related to JASP. So it's a tool. Basically, it's a graphical user interface applied tool. So unlike the case of R, if you want to do some analysis, then you can do all the things just by click. You can import your own data set in the format of CSV or SPSS data file automatically into JASP, just to click file, import. Then once data set imported into your JASP, then you can do like t-test, correlation analysis, ANOVA, regression analysis, just doing click by click, and then you can set up specific options as you want. And now JASP has become a very versatile tool. So now it supports more sophisticated statistical analysis like SEM or network analysis. And surprisingly, the most up-to-date version of JASP supports machine learning. It's amazing. So all the things can be done very straightforwardly, and then everything can be done very easily. But this is available for free for everyone. So let's think about the case of SPSS. I think that the majority of you are currently playing with the SPSS. I'm gonna say it's a pretty easy to use tool and then very feasible. But the issue is that you have to pay for SPSS. Now, as a student or as a person affiliated to an institution, I think that your institution is gonna cover your SPSS license fee. But let's see what's gonna happen once you graduate from or once you separate from your current institution. You have to buy your own SPSS license. The issue is that it's super expensive, developed by IBM. So it's kind of a very tricky tool to buy, because if you are not a student, in order to buy kind of perpetual license, then you have to pay like at least a couple of $1,000. Or even if you can rent the tool on a monthly basis, still you have to pay like hundreds of dollars per month. That's just super expensive. So, because we all are poor students or poor junior scholars, in order to save money, we need to seriously consider moving from SPSS to JASP. The issue is that ideally, you are gonna move on to R to deal with the replication crisis and then to improve open science. But the issue is that R is a super tricky to learn at the beginning. So I feel like the JASP is kind of good intermediate tool situated between SPSS and R because it has a user-friendly GUI. And then it's very flexible. Let's think the case of SPSS. The most up-to-date version, recent version of SPSS supports some basic Bayesian analysis. But the issue is that SPSS is basically primarily suitable for classical analysis. JASP supports both and strongly Bayesian basis. And plus, I think that some of you are interested in doing SEM, structural equation modeling, or CFA, conformative factor analysis. So of course, you can do SEM or CFA with a SPSS, but the issue is that in order to play with the SEM with SPSS, you have to buy a toolkit named Amos. That's super duper expensive. However, JASP is a flexible free tool, so you can do the aforementioned functionalities for free. So it's a super awesome. Please consider downloading and installing JASP on your computer because of these reasons. So what I'm gonna do today is that because there's a time restriction and I don't have any prior knowledge about your background in statistics, quantitative analysis methods, and I don't know how much you are super savvy about both classical and Bayesian analysis. So let me just briefly introduce very crude, simple main concepts of Bayesian analysis. Again, here's a disclaimer. I'm not gonna delve into theoretical further details today. If you are curious about theoretical further details, then please consider taking more specified classes, or I may also consider creating a new workshop dedicated to a slightly more advanced or intermediate Bayesian analysis in the future. But for now, let's focus on basis. And then we are gonna do very simple JASP and R exercises. And I hope all you enjoy a fun time today, if it's possible. All right, then let's start with very basic ideas of Bayesian statistics. So let me start with philosophy of science. So is there anyone who knows what this picture is, what this artwork is, where it is, etc.? Please use the chatting window if you know the answer. Even if it's not a class for credit, I'm gonna give you a kind of just a virtual empty brownie point if you can figure out what this artwork is. No brownie point, no answer, no brownie point. Oh, fraud, that's correct. Yeah, Raphael, yeah, the artwork was created by Rafaela. And then, do you know what the overall theme of this artwork is? Yeah, correct. Yeah, Fred and Lisa, both of you guys got 0.01 extra brownie point for today. Congratulations. And I'm not gonna be surprised at all. With the fact that Lisa provided us with the correct answer, because this is the artwork showing the school of Athens, showing ancient Greek philosophers as well as scientists. So once you see, okay, this artwork is drawn by Raphael, as Frost said, and then it's now in Sistina Cathedral. I don't know the exact name, but it's now available in Vatican. So if you have any plan to travel Rome, Italy, Vatican after the end of the COVID-19 outbreak, please consider visiting this place to enjoy this great artwork. So once you see at the center of this artwork, there are these two guys. The guy on the left-hand side is Plato, Platon, and then the guy, younger guy, at the right-hand side is Aristotle, Aristoteles. So Plato pursued a kind of ideal knowledge. So he said that we have kind of totally objective, pure, not at all contaminated knowledge existing out of the world we are currently living in. So he named that kind of ideal virtual world as eidos, or idea, ideal. So he argued that once we do some research or studies, then we are likely to deduce some new knowledge or ideas from the, ideal knowledge existing out of the world. On the other hand, Aristotle was interested in how we acquire knowledge, ideas through tests and then observations. So he argued that in order to construct the knowledge, of course, there may be some objective knowledge existing like out of the world, but Aristotle emphasized that we are gonna acquire knowledge through experiments or observations. That is pretty consistent with Aristotle's moral philosophy. He emphasized that we acquire virtues and morality through training. Just for information, I'm interested in moral education, even though I'm not a moral guy. Okay, so Plato emphasized idea, while Aristotle emphasizes the reality and observations. So once you see what usual scientists are doing in the reality, let's set aside, let's don't think about mathematicians at this moment. You can realize that scientists are starting with the setting of hypotheses, do observations or experiments, collect data, do tests, and then update their knowledge by confirming or rejecting hypotheses, etc. So once you see the reality, then you can realize that we are doing Aristotelian thing rather than Platonian thing. So the basic assumption of Bayesian statistics, Bayesian guys, pretty similar to Aristotelian idea. So Bayesian guys argued that, okay, we try to observe something and we try to get some idea about what the parameter is, but the issue is that the parameter that we want to observe, discover, so under uncertainty, and then the parameter exists in the format of probability. So Bayesian statistics aims to quantify that uncertainty surrounding our hypothesis testing and inference. So we are gonna start with a certain prior belief or a certain prior knowledge, collect data, and then in order to estimate, in order to calculate the the parameter of interest, we are going to update our prior knowledge based on data, and then try to get a kind of more up-to-date, updated, more realistic posterior belief at the end. So it's gonna governed by whether or not we observe a kind of phenomena, situation confirming our prior knowledge or rejecting our prior knowledge. So that's the way how we update our prior knowledge into the format of posterior knowledge within the Bayesian framework. So it's kind of illustration of Bayesian inductive cycle. Unlike the case of Platonian way of thinking or reasoning, it starts with the prior knowledge and then do observations and update posterior knowledge at the end. So it's kind of pretty realistic process, not deduction, it's induction. So I have briefly babbled about the basis, philosophical basis of Bayesian statistics. Now I'm gonna move on to how Bayesian guys are estimating the parameter of interest. So let's think about, like, we wanna see the mean of a certain data set. You know that it's impossible to collect the data from the whole population, because let's think the case of, like, for instance, the mean house income in the United States. Okay, now many people are working on the what's the name of this event? Collect the data from the whole population. I forgot the name. I completed it.
COVID? Are you talking about Corona? COVID-19?
No, not COVID. I mean the collecting data about the houses in families in the United States happening this year.
Census.
Pardon?
Census?
Oh, right? Census, correct. Okay. I forgot that. I realized that after the outbreak of COVID, I forgot the flow time and my brain is melting down. So I forgot the words. Thanks a lot, Mona. So yeah, now the census is happening. So in order to collect the data from the whole population, then it's a tricky. The census is super expensive. So once you do your own research based on kind of empirical data, then you are likely to collect the data from samples. Then you would like to estimate the kind of the parameter of interest, like the mean household income based on the sample that you collected. So you want to estimate the mean of the population, the whole population. But the issue is that, let's think about the classical guys, not Bayesian guys, frequentists. They assume that there is a kind of a fixed ideal parameter, hypothetical parameter, and then they are mainly interested in whether or not the collected data is somehow extremely deviated from a kind of hypothetical distribution of the population data based on the estimated or ideal parameter of imagination. Okay, here's the point. If we wanna do a kind of estimation based on the frequentist perspective, then the explanation is getting pretty long, because they are doing pretty different from what we really want to do when we are doing estimation. Because once they do estimation, they are going to start with a kind of imaginary or hypothetical parameter of a kind of the whole population, rather than doing a kind of a real updating of the posterior parameter based on data. Oh, okay, it's a super complicated. So let's move on to Bayesian parameter estimation. It's way more straightforward Okay, so Bayesian guys assumes that, because it's super tricky to collect the data from the whole population. So they think that the parameter of interest of the whole population exists like the probability distribution. Not fixed, but still can be updatable and exists in the format of distribution rather than a kind of hard fixed one point parameter. So when Bayesians are estimating the population parameter, they start from a kind of prior parameter, do observation, and then update the posterior distribution based on the observed data. So you can see the rule of thumb of Bayesian guys that here, posterior is getting updated from prior based on updating factor, which can be calculated by observed data at this moment. So this equation shows Bayes' theorem, which was initially proposed by Reverend Thomas Bayes. So once you try to estimate parameter of interest, then at the end you are gonna see the updated posterior distribution and posterior parameter, which is calculated by Bayes' theorem with observed data. So this graph shows how prior can be updated to posterior knowledge through I'm gonna go previous slide. Through observation. So let's think about this example. Sorry, at the beginning, it starts with a kind of prior distribution, which was centered around 0.5, assuming that the parameter is most likely to be 0.05 at the beginning, but once they repeat observations of the data, that they ended up with posterior distribution centered around somewhere around 0.35. So in this example, we can realize that the most likely parameter of the whole population is 0.35, not 0.5 as the prior distribution says. So in the case of classical parameter estimation, frequent parameter estimation, they don't change or update this. However, Bayesians are interested in how things are updated over time. Okay, I accidentally saw the chatting window and Fred was asking about, does the probability of prior means probability of the hypothesis being correct? So that's a really great question. So that question is not going to be addressed at this part because we have been talking about Bayesian updating and Bayesian parameter estimation. We are now move on to Bayesian hypothesis testing, and hopefully this part can address your questions somehow. So let's start with basic ideas about hypothesis testing. Let's see what frequentist guys are doing. Okay, step one is identical across all around the world, both frequentist guys and Bayesian guys are doing this, setting up a hypothesis, either H0, maybe like null hypothesis, and H1, alternative hypothesis, and collect data. And frequentist guys are calculating the p-value. And let's see what happens. Let's think of the case of, let's assume that you are playing with SPSS. Once you see p-value smaller than 0.05, once you see some stars, then you're going to be super happy. Once you fail to see any stars, then you're going to be super unhappy because p is greater than 0.05. However, it's a super tricky, super arbitrary. What's you gonna do once you see p 0.051? Are you gonna be still unhappy? What about 0.0501? And what if 0.05? Oh, indefinite numbers of 0 and 1. That's super tricky. In addition, the interpretation of a p-value is somehow super tricky, murky. Okay. Now I can see the list of participants here, and I feel like you can use some functionalities like virtually raise your hand or do thumb up or thumb down. Mona, can you test whether you can raise your hand?
Yeah, sure.
Yep. Okay, I can see that a couple of guys are raising hand. Fra, please stop doing it. Okay, thanks a lot for checking with me. Fra, you are super amazing. Okay, so I'm gonna give you a quick question about the p-value. So once you feel like a yes, then please raise your hand. All right, let's see. You found 2 stars from your SPSS window, indicating that the resultant p-value that you saw was 0.01, just 1%. Okay, here comes my question. Do you think that it does mean that your alternative hypothesis is likely to be the case for 1% of chance? So does that mean like, oh, sorry, reversed way, okay. Does 1 p 0.01, does that mean that your alternative hypothesis is likely to be 99% truth? If you think so, then please raise your hand. All right. Oh, you are spoiled. You're always spoiled. You only know lots of things. Well, do you have anything to say?
Did you say me? Did you ask me?
Oh, because I said that you turned on your microphone. So.
Yeah. No, I don't have anything to say. I'm not raising my hand. Is what I'm saying. So I'm not agreeing.
Nobody did raise your hand. Oh yeah, it's a super tricky question. Okay, yeah, that's kind of misinterpretation of p-value. Unfortunately, even though we are utilizing p-values to test our own hypothesis, p-values don't say anything about whether or not your hypothesis is true or bullshit. The p-values only say about, okay, the explanation is a super tricky, complex, and maybe my explanation may be incorrect. Then that fact may show that even Hyemin cannot fully understand the real meaning of p-value, so it's somehow dangerous to rely on p-value because it's super tricky to utilize a kind of a tool that you don't understand completely to be utilized in your research. Is super dangerous. Okay, so p-values say whether or not, to which extent your observed data is super extreme compared with the hypothetical distribution based on the hypothetical fixed parameter. Super tricky. At the best, p-values can say something about whether or not you can reject your own null hypothesis. Unfortunately, it doesn't say anything about whether or not you can accept your alternative hypothesis. So it doesn't directly test hypothesis, unfortunately. But interestingly, once you do Bayesian hypothesis, then the resultant Bayesian indicators directly say about whether or not your alternative hypothesis can be supported by data. It's totally opposite to the p-value. And then it can tell you which model, for instance, like which regression model, which regression model with which coefficient, which independent variables is the best model among all the possible models. So Bayesian hypothesis testing can be a kind of more direct tool in hypothesis testing compared with a frequentist p-value based no hypothesis significant testing. So in the case of JASP, once we do some test with the JASP, then we are gonna see a Bayes factor as the result of Bayesian hypothesis testing. And Bayes factor is showing us to which extent the collected evidence, collected data supports our own alternative hypothesis against a null hypothesis. So Bayes factor directly says the strength of belief about hypothesis. So it's very direct compared to the p-value. So this is how to calculate Bayes factor based on Bayes theorem. So basically it's a super complicated, but Bayes factor is a ratio of posterior model O's. So these two are about so for instance, this one shows whether or not hypothesis 1 is likely to be the case given collected data, while this one shows null hypothesis is likely to be the case given data. So Bayes factor is a ratio of this one to this one. So by comparing this numerator and this denominator, we can calculate the ratio of the strength of our belief or likelihood of two different hypotheses. It's pretty intuitive and pretty direct hypothesis testing. So related to Frad's prior question, so this one is only tells us about the distribution of prior knowledge. It is not about whether or not a certain hypothesis is likely to be the case. It only shows us like, oh, before observing data, I think that I'm imagining that the parameter of interest, like effect size, is centered around 0.5 or something like that. It is only about distribution, not about whether or not a hypothesis is likely to be the case. This is about the likelihood of the hypothesis is true, the case. So these two are different from each other. So when we are testing a hypothesis based on Bayesian statistics, and once we utilize Bayes factor as an indicator, then we are more likely to be interested in these guys instead of prior distribution or posterior distribution per se. Fred, did I answer your question? Okay, great, thanks. So once we, okay, let's say that once we found that the ratio of these guys became 4, then that says that Bayes vector is 4. The data are 4 times more likely to occur under hypothesis 1 than under hypothesis 0. So it says that, crudely speaking, the data is more likely to support the alternative hypothesis against the null hypothesis, and then the degree is 4. So that is the basic idea of Bayes vector-based Bayesian hypothesis testing. So if you are interested in testing whether the null hypothesis is the case against the alternative hypothesis, then that's going to be totally reversed. So if you calculate a certain Bayes vector, then you can interpret the meaning, like in terms of the strength of evidence, utilizing some guidelines provided by Jeffrey Rafferty et al. So in the prior case, you found that the Bayes vector is 4. That says that the evidence somehow supports H1 against H0 moderately, positively, but not that strongly because the value is just 4. So if you found Bayes vector like 101, then you can say that the evidence is super, super, super strong. So it's totally different from p-value. It can be directly applicable to a hypothesis testing. So this is the case showing when the resultant Bayes vector is 4. So given the data, it shows that H1 is 4 times more likely to be the case compared to the H0. Once Bayes vector becomes a 32, then the strength of evidence supporting H1 becomes super, super greater than the prior case. So if you are curious about how to plot these pie charts, these guys can be automatically plotted with JASP, so no worries. So for the interest of time, we are gonna skip this. So let's play with some concrete examples, JASP and R. Because everything is gonna get super complicated once I try to introduce many sophisticated testing. For the interest of time, let's focus on t-test. Okay, I'm gonna share my JASP on the screen. Okay, folks, can you see my JASP here? Mona, can you see it?
Yep.
Okay, cool. Yeah, so I think Mona shared the data file with you folks. So let me import the same data file using JASP. So once you click the pull down menu button, then you can see open it here. So I'm gonna import the file from existing in my computer by browsing.
Just to interject, the data file is on the MES website, but I'll share it again.
Yeah, test.csv. It's a CSV file, not SPSS file or JASP file. So it can show that you can feasibly, conveniently import a CSV file in JASP without any hassle. Then once you import the data, then you can see, okay, almost identical to SPSS in terms of a graphical user interface. So if you are savvy about SPSS, then you don't need to spend extra time, extra hours to get refamiliarized with the JASP. So that's a good point. So it shows something like the age of participants, gender of participants, some scores, etc. These variables are about moral psychology. To save time, let's forget about the meanings. Okay, so let's start with comparing means to different groups. So you can do both classical t-test as well as a Bayesian t-test. So let's start with independent samples t-test. Okay, you are interested in comparing scores between two genders. So let's compare MGM score with student t-test. So it says that p-value is super small, maybe super significant. And at the same time, you can add other variables to be compared as well. So I realized that it's somehow much fancier than SPSS because lots of things can be done online. Okay, so if you're interested in coherence, you can calculate coherence as well. And then confidence interval can also be displayed by just by clicking the options. And if you're interested in testing normality using Shapiro wheel, then you can do these kind of things as well. Unfortunately, some variables are not normally distributed. And then also, you can also test equality of variances. So if you find like, there's an inequality of a variance, then you may need to non-parametric testing method instead of parametric testing method like a student. So on JASP, you can do Welch test as well as man-and-Whitney non-parametric test at the same time, just clicking options. So it's just super simple. So we completed all the classical analysis. Then we can do the same things with Bayesian analysis as well. So identical, almost identical. Setting a group variable, and then you can simply add variables to be compared. Then you can see the resultant Bayes factors here. For instance, in the case of MGM, the resultant Bayes factor is just 5. Once you see the result from classical analysis, the p-value was super small, so you can easily think that, oh, I got very strong result supporting the alternative hypothesis. But once you do the same thing with the Bayesian test and then check the Bayes factor, then you cannot be super happy with that because the evidence is not super duper strong, just moderate according to Jeffrey's guideline. So I realized that I became, much more humble once I started using Bayesian analysis. Okay, so I'm gonna show you how to create some plots showing pies as well as changes from the prior knowledge to posterior knowledge. So once you click this option, then you can see the same type of pie chart that I displayed in the slides. And then you can also see how the posterior knowledge has been updated from the prior knowledge. Okay, so in this case, because we are interested in whether or not the effect size was a non-zero, we utilize prior distribution centers around the zero, indicating that there would be no meaningful non-zero effect. So yeah, so it ended with updated posterior pretty different from zero at here. So in usual cases, once we want to test whether or not there's a significant difference, then we are likely to use the posterior distribution center around the zero. Okay, that's a brief introduction to JASP. So if you are interested in doing a kind of correlation analysis, then the correlation analysis can be done very easily. And if you want to indicate some correlations, which correlation coefficient which is greater than the threshold proposed by the guideline, then you can automatically flag big correlations as well. Okay, then let's close the JASP. Oh, let's leave it as it is because a couple of folks posted questions about JASP. So I'm gonna leave this as it is. Let me just move on to our screen. Okay, I'm gonna reshare my R Studio. All right, can you see my R, Mona?
Yes, yes, I can. I keep forgetting I'm on mute. Yes, I can.
Okay, appreciate that. All right, so these functionalities are implemented in a package named Bayes Vector. So in order to do JASP-like things on R, then you have to download and install Bayes Vector library. So I'm gonna import Bayes Vector to my computer and then import test.csv. Then I'm gonna do a classical test using t-test. Then R is gonna display the result of a t-test here, showing that MFQ HC is significantly different across two genders here. The same thing can be done Bayesian t-test as we did in JASP by using t-test BF function implemented in Bayes vector. So it shows resultant Bayes vector here, 184, something like that. Once we compare MFQ HC across two genders, then the difference of the means pretty strongly, very strongly supported by the evidence. Okay, let me share another thing. Okay, here's the result from R with Bayes vector, 184, something like that. Let me show you the result from JASP. Okay, identical 184 once MFQ HC was compared across two genders. So in default, once you don't change any options, then JASP and Bayes vector package will produce the identical outcomes. So here's my suggestion. If you feel like you are pretty familiar with SPSS and uncomfortable with computer language like R, composing your own script, then you may start with the JASP at first. If you feel like yourself is a super savvy about computer language, R, Python, etc., then you can just directly start with the Bayesian factor implemented in R, because by composing your own code, you can have the greater degrees of freedom to do your own tasks of interest. Okay, this is the end of the lecture and some demonstration. Now, I'm gonna answer the questions that you posted. Okay, let's start with Corinne's question about statistical assumption. Okay, Corinne, could you be able to repeat your question once again for other folks?
Hi, so Dr. Han, so my question was in like the frequentist theory or model, you have to have some sort of statistical assumptions before you conduct, for example, regression analysis. So I was wondering, like for Bayesian analyses, do we have some kind of prerequisites to do this kind of analysis?
Okay, that's a great question. So basically, in principle, Bayesian analysis is way more free from that kind of strong assumption compared with classical analysis. Because in the case of a frequentist test, you are assuming a kind of hypothetical parameter and hypothetical distribution to calculate p-value. But in the case of a Bayesian analysis, you are updating the distribution of your like probability or likelihood posterior distribution based on the data. So once you repeat the iterative procedures of observations and then update posterior distribution, then the calculated posterior distribution can be somehow deviated from the normal distribution. So that says that Bayesian analysis in principle doesn't require the normality assumption as a prerequisite of analysis. Of course, in order to do hypothesis testing ideally, then you may need to choose proper priors. But in general, Bayesian testing is way more robust against a normality of data set, data distribution. And then I found such a point from my previous studies, and then those points are presented in my prior articles that test comparing classical versus Bayesian analysis in terms of their robustness. Did I answer your question, Corinne?
Yes, thank you.
Okay, no problem. And Ian, you sent me private messages. So could you be able to vocalize your questions, please?
Sure. So I have a couple questions. The first one, I might be taking this whole Aristotle thing a little bit too seriously, but you were talking about how one of the important factors is to have this prior distribution and prior knowledge, and we're supposed to update that. And so it sounds like one great way you can use Bayesian analysis is to have a previous study, let's say, that found a result or had some kind of means, and you're testing a new theory based on that prior knowledge. But in your, and then you update that knowledge, right? But then in your example, you just took new data, you have males versus females, and there doesn't seem to be any prior knowledge at all. It's just testing new data And so it seems theoretically more like frequentist. I'm just going to compare two distributions as opposed to, oh, I have a prior stance or prior evidence of whether there are sex differences. I'm going to enter in my distribution and my prior knowledge about whether I think sex differences exist based on previous studies, and then test that based on this new data. There was no prior evidence that you put in. It was all like post hoc driven. And so that seems very conceptually at odds with this whole idea of needing prior information and prior distributions in order to do these analyses. So I wonder if you could clarify that.
Yeah, that's a great question. So in the cases of the tests that I introduced in JASP, basically interested in whether or not there is a non-zero difference. So it was necessary to start with the assumption that, oh, there would be zero-centered distribution of parameter like the effect size, and then observe the data iteratively, and then end up with a kind of posterior distribution centered around the realistic effect size observed from data, and then compare that posterior distribution versus prior distribution centered around the zero. So in this case, it started with prior distribution, like based on the null hypothesis. So maybe slightly different from what you pointed out, because in the case of like using a more informative prior based on the prior studies, then you are gonna test whether or not when you observe from your own current data set is significantly different from the previous studies. Does that make sense?
Yeah. So I guess you can do it both ways is the question, and the implicit prior is a kind of a null distribution, which sounds just like classical hypothesis testing, when you have a null hypothesis saying that there's no difference, and I'm going to propose that there is some difference, like with sex or gender or whatever. So in that sense, it sounds, in the way that you used it, it just sounds so much like a frequentist approach. I don't see a huge, conceptual difference between the two.
Yeah, but basically, in the case of the testing that I introduced today, many guys are interested in doing like a comparing means between two groups or something like that. But conceptually, even though, like in terms of like what they're doing, classical guys as well as the Bayesian guys are doing the same thing, like comparing the means of two different groups. But in the case of the resultant statistical indicator and how the statistical indicator can be interpreted, conceptually, those are totally different, p-values versus space vectors. I think you can agree with me the point. Right.
Yeah.
So, yeah, go ahead.
I was just going to say, my second question actually is related to that too, in that in frequentist classical testing, like you said, Cohen's d is kind of a measure of the strength of the effect, and we all know that you can have p-values that are very strong, but yet Cohen's d is it's very small, suggesting that the effect size isn't very big. And that almost sounds like this Bayes factor, where you can get a strength of evidence that's very strong or not very strong. And I'm wondering, is there any correspondence between a Cohen's d like big effect and a high Bayes factor? Are they correlated with one another, or are they completely independent from one another?
That's a great question. So let me briefly answer a little bit more about your first question. Can I do that?
Okay.
So
that sounds good.
yeah, I feel like when you're suggesting about like utilization of the prior knowledge collected from the previous studies can be applicable to like the recent projects related to the big lab replications. I think you are familiar with what they are doing right now. Replicating.
Yeah, I think in some cases they are using that approach. Yeah, exactly. But given that ideally you want to have some kind of prior knowledge and update that, I guess it's just not, when we are designing experiments that are new, it doesn't seem like we know what the prior knowledge is always. And so to me, it doesn't always seem like this method would be as applicable if we're starting from scratch, like we don't know what the prior knowledge is, or the studies were so different, you can't use their means or distributions to really set an a priori prior knowledge to have informed priors. And indeed your examples with sex, you get the same answer whether you use a statistical classical inference or you're using the Bayes. One is just giving you kind of, oh, this is strong evidence versus weak evidence, and the p-value is, oh yeah, you can use the t for the same thing. Oh, it's a big T, it's a little t, so that's big evidence or low evidence. Even though they're different, they seem to be pointing in the same direction. So I'm not convinced one way or another with those examples.
Yeah, basically p-values, natural p-values and Bayes factors are going toward the same direction, because once you see the real strong effect size, then p-value is likely to get super small, while at the same time Bayes factor is getting super great.
Okay, so there's in many, probably not in all cases, but in a lot of cases, they would actually point to a similar story, you're saying.
Yeah, that's true. If they are directing toward the two different directions, then something is wrong with the software or your analysis script or something like that.
Okay.
And then you know that I'm working on how to utilize multiple, how to implement multiple comparison correction in Bayesian fMRI analysis. And I found that in order to ideally create ideal prior distribution for the Bayesian fMRI analysis with the multiple comparison correction, realized that the prior study is strongly necessary. So okay, even though it's necessary to utilize a kind of prior distribution centered around the zero, because we are mainly interested in testing whether there's a significant difference across two different conditions. But in order to shape the proper variance or deviation of that distribution, we have to have the prior knowledge from the previous study. I'm still working on that, but realize that we need to learn from the previous studies to produce the maximal sensitivity as well as selectivity by reshaping the prior distribution instead of utilizing the default prior distribution.
Right. So in the program, I didn't, in JASP, I didn't see, or R, how do you tell the programs, hey, here's a prior distribution or priors that I want to use instead of the default? Is that easy to include? Oh, I see.
Yeah. So if you're gonna utilize the default Cauchy distribution in general, the default distribution is centered around the zero with the scale 0.707. But if you have a strong assumption about your a prior knowledge, then you can change this as well. Given the prior study, I thought that the mean should be centered around the 0.5 instead of 0.0, and then it should be pretty widely dispersed, standard deviation 2 instead of 1. Then you can reshape your prior pretty feasibly. But the issue is that JASP only supports these types of priors to be adjusted on GUI. So if you want to design your own customized prior distribution, then you need to play with a Bayes vector in R.
Okay, that's helpful. And then I have one new question that I didn't post. And so basically, it sounds like using frequentist testing, it may not be ideal, but because Bayes factor does, I mean, that is still the prominent way people are testing ideas. And Bayes factor might give some useful complementary information. Do you see that people are reporting both statistics, like, because it is satisfying to get a p-value and to say, hey, this is significant, but then I could see how it is useful also to say, oh, but we want to know the confidence of our hypothesis and the strength of evidence. So do you see people using both methods in a single paper because they're complementary, or do people really, because they're different camps, they prefer one or the other and not to include both?
Yeah, I understand that. That's kind of really tricky practical question to be addressed in the field. So recently, I had a conversation with a guy who is working as a subject editor at Nature Human Behavior and Royal Society Open Science. The guy specifically interested in the pre-registered reports. So we are able to have opportunity to talk about some statistical guidelines. And then I found that now those journals, specifically pre-registered reports, are not that interested in working with the p-values anymore. So they, in their guidelines, they specify that they prefer Bayes vectors over p-values in the pre-registered reports. So when I asked a specific question about then, where's the use of p-values? The guy answered that you may still use a p-values, but in a complementary way to show that Bayesian analysis was another kind of total bullshit by showing that those two guys are going toward the same direction. So that's the answer that I heard from that person, but maybe specific to either Nature Human Behavior or Royal Society Open Science. But you know that those two journals are field leading journals, so you can realize that it will be a possible way to improve the overall quality of manuscript by doing so.
Cool, that was helpful. Thank you.
Yeah, you're welcome.
Any other questions for Dr. Han? Yeah, I don't see any raised hands. I guess if that is it, then I just want to say thank you, Dr. Han. For participants, don't log off yet. I just have a couple of things, last minute things. I'll post it in the chat as well. Reclaim it. Thank you, Dr. Han, for this very, very enlightening and helpful talk. Thanks to participants, because I think if people are not here, then we're just talking to empty screens. So also thank you to all of you for coming and learning from Dr. Han. I thought this was very helpful. Hopefully it was helpful for everybody else as well. And thank you for all the people who asked questions. Very helpful. Some of those things I didn't think about helped me think about those things as well. So just to reiterate, I've posted these links in the chat box. Everybody can see my screen, yes? Yeah, okay, all right. The left side links are the ones I posted earlier, but it's there again. And I just noticed that there were 3 professors here. And again, this was meant to network, also serve as a networking event. And I just don't know how to do that online. So I figured the best way to do it is to at least give you names. So Firat, Litz, and Ian are here. You heard from some of them either through chat or talk. So I've given you links for graduate students or even faculty who are interested in collaborating with the others. I think all of you know each other, so in this case it doesn't it doesn't help as much. But the idea is to bring everybody together. So that is those are all the links. You can find them in the chat box. And the upcoming one is on Monday. Dr. Bloomfield will be teaching us about evaluating interventions using single case research design. So I know nothing about it, so I'm looking forward to it. And I hope if you're interested, you'll come and join us. Thank you again, Dr. Han, and thank you everybody for being a part of this.
Yeah, thank you very much for the great opportunity, and thank you for coming a lot. Have a great weekend.
Yeah, you too.
Yeah, stay safe and healthy.
Yes, yes, good point, good point. Yes, I always keep forgetting that. Yes, please stay safe and healthy. And I'll leave the thing going on if people want to copy links and so on. But once everybody's logged off, I will close the screen.